All right, today we're taking on graphing exponential functions with transformations. So graph the exponential parent function, then graph each of the following exponential functions using transformations. State the domain and the range. So here, what I want to point out first is that there's more than one exponential parent function. It really just depends on what the base value is. So for all of my problems today, I've selected a base value of 2. But the base value could be 3, could be 4, could be 10, could be any number you want. I'm just picking a nice, easy one to work with. I'm picking a base value of 2. So when I start with my parent function, I will start with a table. Here's my xy. And I usually go -2, -1, 0, 1, and 2. So if I plug it in, first off, I have 2 to the -2nd power. So whenever I have a negative exponent, that means it's going to be 1 over 2 to the +2nd power here. So my negative exponent really just helps me represent a number that is very small. So this becomes 1 over 2 squared, so 1/4. 2 to the -1st power would be 1 over 2 to the 1st power, so 1/2. 2 to the 0 power is just 1. 2 to the 1st is 2. 2 to the 2nd gets us 4. So if you look at the y values, you can see that from stage to stage, we are doubling. 1/4 times 2 is 1/2. 1/2 times 2 is 1. 1 times 2 is 2, and so forth. That's because that base value was 2. So it's going to double from stage to stage. So if I plot the points I have right now, I have -2 right here is 1/4. -1, 1/2. 0, 1. 1, 2. 2, 4. If I had another point, I would have 3, 8, and so forth. So here I have enough information to smooth out my curve, but I also want to remember I have an asymptote. So my asymptote right here is this boundary line that we approach, but we never cross. So let me draw it in. Let me say that another time, and then write its equation. So right here at the y-axis, at y equals 0, that is the equation for it, I have a horizontal asymptote. Let me write it here. And its equation is y equals 0. So my horizontal asymptote is this boundary line that I approach, but I do not cross. So if I think about that conceptually, let's say that I picked a number way over here at -10. If I tried to input that here, 2 to the -10th power would be like saying 1 over 2 to the 10th power. So I'm dividing 1 by a larger number on the bottom. So I'm getting something much smaller. I'm getting closer and closer to 0, but it's not quite 0. So as I move over this way to the left, right, my y values get smaller and smaller and smaller. They get closer and closer to 0 without actually ever being 0. There is no number that I can plug in for x that would produce 0 for y over here. If I plug in even -10,000, that would be 1 over 2 to the 10,000th power. It's still not 0. It's still tiny. It's just still never going to be exactly 0. So when I draw it, when I smooth out my exponential graph like this with that base of 2, I try to draw it so that you can see that we are approaching that asymptote without actually ever crossing it. So this is a good way to write it in, give those arrows at the end, and then just make sure that you're not passing over that horizontal asymptote. Okay, for the domain for an exponential function, you can always input any value for x. So the domain, as we can see, right, we're expanding left to right, domain is all real numbers. If I write that in interval notation, I would use my infinities, negative to positive infinity, in my soft brackets or parentheses, just like that. And then my range here, if I trace it bottom up, I got no y values in here, my y values have to be more than 0. And in this case, they cannot equal 0. So y is greater than 0. Okay, in interval notation, I would say from 0 to infinity, they both get a soft bracket this time. Again, a y value can never be equal to 0 for this type of function. Okay, next up, here applying just a singular transformation. So what am I doing in the first one? I'm applying here a multiplier. So I'm multiplying by 1/2. So this is going to be a vertical compression by a factor of 1/2. Okay, what does that mean? It means that all of the y values are going to be multiplied by 1/2. So my starting point here was at -2 1/4. So if I cut that in half, I'm at 1/8. It's hard to see, but that's just even smaller, a shorter distance than it was over here. Okay, for 1/2, normally I'd be going, or for -1, normally I'd be going up 1/2, but I need half of that, so it should be 1/4 right here. Next, here at the 0, I'd be going up 1, but again, I need half of it, so 1/2 right here. As I go over 1, normally up 2, but I cut that in half, so up 1 just like that. And as I go over 2, normally I would be going up 4. Okay, but I need to cut that in half, so I'm going up 2. So all of those vertical distances, those y values, they just got cut in half because we applied the multiplier, the vertical compression, by a factor of 1/2. So when I connect my dots, right, it looks like this, just looks like it got nice and squished. And then I always want to include my asymptote as well. So my boundary line that we approach, but do not cross. All right, the domain, x can be anything. That's true for any exponential function, so all real numbers. In interval notation, I can say from negative to positive infinity in my soft brackets. Okay, my range, what can y be? Well, y has to be something more than 0. So y is greater than 0. Or I could write that as 0 to infinity, soft brackets, like so. Okay, let me slide it up. All right, next up here, I see that there is a 1 attached to the x in the exponent position. So whenever we see something attached up into the exponent position like this, if I see x plus something or x minus something, that tells me that it's a horizontal translation. So right here is a horizontal translation or a horizontal shift. It tells us if we're moving left or right, and it's always the opposite of what it appears. So this tells me that we're going 1 unit to the right. All right, so my asymptote, my horizontal asymptote, stays in the same spot. So I'm just going to draw that in first. And then for my parent, usually I start over here at -2, up 1/4. But I'm sliding everything to the right. So I'm going over 1 here, and now I'm up 1/4. And then as I go over, now I'm up 1/2, move over, now I'm up 1, move over, now I'm up 2, move over, and now I'm up 4. So every point slid 1 unit to the right. A horizontal translation, 1 unit to the right. Okay, the domain, x can be anything. So all real numbers, or negative to positive infinity in my soft brackets. Okay, my range, as I move bottom up, I see, oh, well, here has to be more than 0. Y has to be greater than 0. Or I could write that as 0 to infinity. They both take a soft bracket. All right, next up, here I have 2 to the x plus 1. So here I see that that plus 1, it's on the outside. It's not attached to the x in the exponent position. It's on the outside. So this tells me it's a vertical translation. 1 unit up. So that means that my asymptote, it's sliding 1 unit up as well. So my new asymptote will be right here at y equals 1. So then when I graph it, I always graph it just like I took my y-axis and just slid everything up 1. So I base everything from my asymptote as my reference point. So normally I start at -2 1/4. So here I'm -2. I'm 1/4 above the asymptote. So I'm 1/4 above. And now as I move over, I'm 1/2 above. I'm 1 above. I'm 2 above. I'm 4 above. And then I connect my dots. Okay, my domain for any exponential function, all real numbers, or negative to positive infinity, soft bracket, both sides. Okay, range, what can y be? Well, now it's changed. So here, right here, I'm at y equals 1, and I'm anything above it. So y is greater than 1. Okay, or I could write that as 1 to infinity. Soft bracket for both, right? Because it can never be exactly equal to 1. That's where I have an asymptote. All right, next up, here I see a negative on the outside. That tells me that it's reflecting over the x-axis. Okay, so my asymptote has not moved. My asymptote is the same as the parent. Let me draw that in. All this means that instead of going up, we're going down instead. So normally I start at -2 1/4, but I'm going to go down 1/4 instead. And then I'm going to go down 1/2, down 1, down 2, down 4. And then I can connect my dots and show that reflection just like so. So again, my domain, right, it stays put. It's all real numbers. It's always all real numbers for any exponential function. Okay, or I could write that as negative to positive infinity in the soft brackets, just like so. Okay, the range, right? Well, the range, if I read it bottom up, I see, oh, well, it can be anything from negative infinity to 0. So really, y can be less than 0. Okay, in my interval notation, I could say from negative infinity up to 0. Soft brackets for both. All right, last variation. So here we have a negative, but it's attached to the x in the exponent position. So that tells me that it's reflecting over the y-axis instead. So I know my parent usually looks like this. So if it's reflecting over this mirror line, it's going to look like this instead. It's going to look like a decay function instead of a growth function. Okay, my asymptote is the same. So I'm going to keep my asymptote right here at y equals 0. Okay, so every point that I usually plot, it just gets reflected over the y-axis instead. So usually I start here. So at -2 and up 1/4. But instead of it being right here, it's going to be over here at +2 1/4 instead. Okay, and then here at -1, I usually would be up 1/2. So instead of being here up 1/2, I'm going to go at +1 up 1/2. 0, 1 is going to be the same. Okay, if I was over 1, I'd be up 2, but I need to reflect it over to here. If I was over 2, I'd be up 4. I need to reflect it over to here. So remember that here our mirror line was the y-axis instead. Sometimes it's helpful to graph the parent function in pencil and then the transformed function in pen. That's also an option. Okay, so then again, when I connect my dots, here is what my exponential function looks like. Okay, for the domain, again, can always be anything, all real numbers, or negative to positive infinity, soft parentheses or bracket, like that. Okay, range, well, again, if I trace it bottom up, I see, oh, has to be something more than 0. So y is greater than 0. Or 0 to infinity, soft bracket, or parenthesis just like that. So for any exponential function, we know that the domain is always all real numbers or from negative to positive infinity if we choose interval notation. Okay, the range, it's usually y is greater than 0 unless we have a reflection over the x-axis or if we see a vertical translation up or down. That's when it changes. Have a wonderful rest of your day.